on time, and we try to do the whole conference, everything on time. We like to welcome you in Leuven for the 30th edition of FSE, which will happen in this modern building for a change. No, you don't hear us? Hello? No? Okay, we have time to fix things, I hope. What about here? Do you hear me now? Better? Okay, okay, I'll use this one then. Now it works, of course. Okay, so this time we are not in the medieval buildings of Leuven. We decided to have something different and to be in this modern building of the Provinciehuis, how they say it in Dutch. So as you know, Belgium is a very beautiful, small, but complex country. We have a lot of provinces and then a lot of administration and a lot of administrative units. And Leuven happens to be the capital of the Vlaams Brabant, the Flemish Brabant province. So this is the building of the Flemish Brabant province. Has been built a couple of years ago, not maybe more than 10 years ago, by a local architectural bureau and a Portuguese architect. You probably have noticed the yellow balcony at the 10th floor of the building, which is something between art installation and something that you can actually use. It's actual balcony, and we have a proof for this. We actually wanted to know, can you step on this balcony? Yes, you can. It has been designed by Aglaia Conrad, Austrian artist, and it's called Het Balkon, which is supposed to symbolize being, I mean, it's actually a balcony where you can go and smoke. That's the basic purpose of it. But it also, you have a very beautiful view to the city. It's one of the tallest buildings in Leuven. And it symbolizes visual, social, communicative, and relaxing. That's what at least the artist wanted to tell us. You have received a conference gift. If you haven't, please pass by the reception and get your gift. So you should have had a t-shirt, a box of chocolate inside of the bag, and a bag. Anything that you miss or anything that you want to ask, you can always pass by to the reception. The reception will be working during the whole conference. Now we are here to work, actually. We have a busy program. We have morning and afternoon sessions. The morning session starts from 9 to 12:30, but please check the program. Not every day you have exactly the same schedule because of invited talks or special other talks. So sometimes the coffee breaks or the lunch are shifted. Please check. In the afternoon, we have from 2 to 5. And between 12:30 and 2, we have the lunch also here in the corridor, a bit further on the left. When you get out of the room, there are 2 foyers, 2 lobbies where the food will be served. Also, the coffee breaks and the lunch are in the same place. You have the RAM session tomorrow, and you will hear a little bit by the RAM session chairs after us to give you some instructions. The website is already on, so you can read there also the conditions. On Wednesday afternoon, you have free time. You can enjoy the city. I hope the weather will be nice. Siemen will talk about this a bit later, what you can do on Wednesday. Important speakers. These are the most important people of this conference. Please upload your slides 24 hours before your talk. And there is no discussion about this. You cannot come with your own laptop or with your USB. You just don't present if you don't have the slides. Please check once you upload that the slides that you uploaded are really the slides that you meant to upload, because we saw already for today so the last session of today, there is one talk which has slides with a different title than what is in the program. We don't know what happened, but please check. And there is one missing for today, for the last session. I don't know the names, I don't want to say names, but please make sure that all your slides are uploaded. If you speak tomorrow, before you leave the room, please upload your slides. Even you should have done it already, actually. You have a session chair for each session. Please find out who your session chair is and talk to him, present yourself so that you can say your name, how she or her or he has to pronounce correctly your name. The session chairs, you can sit here. We have a computer for you where you have to also watch the questions from the Zoom, because we also have some, not too many, but some remote participants. So please, session chairs, look at the chat and see if there is any question from there. And you have to repeat it because we don't put the sound for the Zoom to come in the room. And of course, try to stick to your budget of 17 plus 3 minutes for questions. For the audience online, I don't know if anybody is online already, but please post your questions in the Zoom chat. You will not be able to speak, and the session chair will read your questions. So this was all the serious part. Now the fun part is to Siemen.
All right. So for the social events, already yesterday, many of you visited the Irish College. I hope you liked it. Hope it was good food. I have some more good news. So tomorrow there will be the rum session that Svetla already talked about. There will be snacks, there will be drinks. Now listen carefully, I will say this once. Sadly enough, you cannot bring the drinks inside of the auditorium. We're watching you. And now on Thursday, you'll have a banquet. This is a very nice venue, hopefully again, good food. But important here to remember is to bring your badge, because this will serve as your entrance pass. So don't forget about that, so you can enter easily.
Diet restrictions?
Right, so if there, thank you. For those that have diet restrictions, you should have gotten a colored card. This is just to signal the waiters to get you the food that you need. If you didn't get this card, you can always come and talk to reception. Now on Wednesday, we have a free afternoon. You can do more research with your colleagues, or you can take a break. If you are taking a break, please check in the website under the technical program, all the way at the top. There is the FSE booklet. On that booklet is a lot of information. You can visit the Great Beguinage, the University Library, the City Hall, and the Arenberg Castles. These are very, very nice places to visit, and I hope the weather will be good. And also there is the Oude Markt, the old square, literally translated. This is a square just next to the City Hall, where there's a lot of cafes, where you can definitely have a lot of fun. Now, so as I said on Thursday, there's the banquet on the FSE website. You'll find where the banquet is. It's just 20 minutes walking from here. You'll see, the address there. Logistically, you'll find that there's people with yellow t-shirts walking around. You'll notice that these are not only worn for pure pleasure, but they're also there to signal you who to talk to. So definitely ask them for questions, or ask Svetla or I if we can accommodate your conference. If you didn't know already, welcome back to the online world. We also have an open public network on FSE 2024. There you can connect for Wi-Fi. And finally, I want to thank to all of our sponsors that make this event possible, that make sure that you guys have even better food. Visit their booths. They'll be more than happy to talk to you. You'll find this slide during the breaks also with all of the sponsors for this event. We thank them. And now I'll leave the word to our rum session chairs.
Thank you, the sponsors. The rum session chairs, you want to say something?
That's it in the front, right?
Yes.
Okay, so Gaëtan and I will be rum session chairs. I didn't prepare any slides, but the information is on the website, so be early because the rum session is ready tomorrow at 3:30. We welcome serious talks for 1 to 4 minutes, and funny talks you can get an extra minute. If you check the website, you can also earn a bonus minute if the PDF of your submission hashes to a digit with the last 7 characters being F5E 2024. There may even be a special prize if you can do this for 2 hash functions, for SHA-1 and MD5. There will be more prizes. There will be a quiz. So the number of questions in the quiz depends on the number of submissions you make. So I really invite you to send stuff. The deadline is tomorrow at 10 a.m. But you can still update your slides till 1. So we need a bit of work to fix everything. But you can finish your presentation until 1. I don't know, do I have to say more, Gita? Yes. Yeah, so just at 1 we need the slides because then we're going to combine everything, but we need to know if you want to give a talk before 10 a.m. Right? So that's it, right? Okay.
Thank you. Okay, and now we start with the first session. The session chairs. The session chair is Orr.
Welcome everyone for the first session of FSE. Let's thank the general chairs for all the hard work that they have done so far. So, the first talk of the day won the best paper, one of the best paper awards, cryptanalysis of half-loop block ciphers destroying half-loop 24 by Gregor Leander, Shahram Rasoolzadeh, Lukas Stennes, and Lukas is going to give the talk. Lukas?
Yep. So NATO and US military use an insecure encryption algorithm called half-loop. In this talk, I will show you how a simple differential attack totally destroys the cipher and allows for practical key recovery attack. But first things first, so as already said, the paper is joint work with Gregor Leander and Shahram Rasoolzadeh, and of course, we are honored that our work has been selected as one of the 2 best papers. Okay. Then, I mean, when you see this picture, maybe some of you think it's because of, I mean, the cipher is a military cipher, right? So it's used in military application. That's maybe why I include this picture of a tank. But others might remember, right? Because this picture I actually took 2 years ago at FSE 2022 in Athens. So it happened that the same time the conference took place, there was also the national holiday of Greece, and they celebrate with a military parade, and that's where I took the picture. And actually I include the picture in the presentation because it's somehow the start of the story of the paper, because also in Athens, Markus Dansari, so co-author of first paper on breaking half-loop, gave a talk on the so-called SODAC encryption algorithm, which is the successor of, the predecessor of half-loop 24, so the cipher that was used before in this military application. And in his talk, Markus then pointed out that there's this new encryption algorithm half-loop, and after this we started to look into this, and then I presented this paper last year at FSE 2023 in Kobe, and after the talk there, it was actually Shahram who then reached out and said that he thinks that we can improve the attack, and then he was luckily very persistent about improving the attack, and that's why I'm here today. Okay, so let me briefly explain why we need this, or why the military needs or designed this half-loop cipher. So it's used in high-frequency radio. And high-frequency radio, I mean, the idea is that you use some specific frequencies between 3 megahertz and 30 megahertz, and then like those radio waves will be reflected by the atmosphere, right? So a signal, if Alice sends a signal, it will be reflected by the atmosphere, and then actually can be reflected by Earth again, and it will travel around the world, right? And this is called skywave propagation. And then this then enables communication across very large distances, and of course, this is something that the military is very interested in, but also I mean, some others might be interested in as well, as diplomatic service or disaster management agencies, because it enables communication without any external infrastructure, right? So you don't need satellites, you don't need cell towers, you don't need nothing. And then inside this high frequency radio, half loop, so this trickle block cipher, is used to encrypt handshake messages. And we will come back to this later. Okay, so let me briefly explain how half loop 24 works. But notice that there are actually 3 versions of half loop. So half loop 24, 48, and 96. And the number represents the block size of the tweakable block cipher. And there are 3 versions because in the underlying protocol, so in this high frequency radio, there are 3 different protocol versions and they need different block sizes. And that's why there are 3 versions. In the talk, we will stick to half loop 24, but of course the other 2 versions work similar. Okay, so let's have a look at the big picture first. So half loop, it's a tweakable block cipher, right? So 24, so 24-bit plain text, 24-bit ciphertext, and then a 128-bit key and a 64-bit tweak. And the tweak actually consists only of the current time and the word counter and then the frequency being used in the radio application. And therefore it's implicit, so you don't have to send a tweak, so both parties will just know the tweak without it being sent. And then I already mentioned half loop supersedes the so-called SODAC cipher, which is the cipher that Markus gave a talk at in Athens. And actually this one was only a 56-bit cipher, so that's already quite questionable because this half loop was only designed in 2017. So up until then, a 56-bit cipher was used. Okay, then, I mean, you might, so the people who have been last year at FSE might recognize it because I gave a talk about breaking half loop there, right? And then you might remember that half loop is actually very similar, or let's say heavily inspired by AES, right? So we have the same S-box, we essentially have the same key schedule. And then, like, if you think about AES, you usually represent the state in this 4x4 matrix, and then for half loop, we shrink it down. So it's only a 3x1, and then for the larger versions, we extend it again. And then it also has 10 rounds, as same as AES 128, and this already is quite a questionable design choice, as you will see in a minute. So this is the round function of half loop. So we, everything standard. So we have key addition, S-box. Then those shifts are a bit strange. We could include them in a mixed column matrix, and that's actually what we do. So whenever you see this L, that's just a linear layer. But I mean, the S-box and the mixed column operations, those are sound, right? The S-box, AES S-box is of course strong, and this mixed column is also MDS. So the building blocks of the round functions are strong, but we only do 10 rounds, right? And we have 24-bit round keys. And then there's already, I mean, you have 11 of 24-bit round keys, so only 264-bit of round keys. And I mean, if you are aiming for 128-bit security, then you, I mean, I won't go into details, but there will be meet in the middle attacks, right? Okay, so but let's go for the more important stuff for our attack, and that's the key schedule. So as a reminder, here's the AES key schedule, right? So we take our 128-bit key, and then we have this file-select structure to derive the next round key. And then we would do this again and again until we have all our round keys. But for half loop, I mean, there are only 24-bit of round key, right? So we simply take the first 24 bits as the round key 0, the next 24-bit, and so on and so on. And then we only need one of this like file structure, and then the beginning of the second one to get the last byte of the last round key. But that's not the only difference. So the other difference is that we add the tweak here, right? So it's a tweakable block cipher. We have this 64-bit tweak. And what do? We simply add it to the first 64-bit of the key, and then use the cipher as before, like block cipher. And that's not only a questionable design decision, this is actually straight up bad. And this was already pointed out by Liskov, Rivers, and Wagner at Crypto 2002. So actually in a paper that introduced tweakable block cipher, it says if you just add the tweak to the key, it's in general not secure. And then in the paper that I presented last year, so DDLS, that's Markus Sansari, Patrick Derbez, Gregor Leander, and myself, we already pointed out that there's a generic attack, and so this is the first attack that I want to present. It's quite simple, right? So we have a tweakable block cipher. I mean, it's generic for all half-loop versions, and also just for all tweakable block ciphers where you simply add the tweak to the key. And for convenience, let's split the key into two 64-bit strings. And then what happens inside of half loop is essentially this, right? So we have this block cipher E prime, and inside the tweakable block cipher E, and then we XOR the tweak and one of the keys, and then we feed both keys. So those are concatenated into the block cipher. And then what do we do? So for an attack, we have this online phase, and we need a table, so maybe a hash table or just a sorted list, whatever you prefer. And then we enumerate all K prime and encrypt with this E prime some plaintext or choice, right? Under the key 0, so the first 64 bits are 0, and then this K prime, right? So this part is 0, and then the K prime part, we enumerate all of them. And then we store P and C, we store, of course, C and K prime in the table, and then the only, like, the important thing about the table is that we can efficiently check whether there's a C in it already, and then we store the K prime. That's actually then, of course, what we do in the online phase. So we enumerate all the tweaks, and then we query the encryption of the same plaintext as before with this tweak. And then if we do this for all tweaks, at some point we will encounter that the output of this XOR is 0, and then we are in the case as in the online phase, right? And we can check for this by checking whether the C is in the table, and if so, we have this key candidate. And of course, there are some trade-offs to this, right? We can use less operations in the offline phase, or of course, we also for the small version for half loop 24, we need more plaintext and ciphertext, right? Because it's only 24-bit, and we are going after a 128-bit key. And for all those details, I refer you to the paper. Okay, so let's have a look at the attacks so far against half loop 24. And I mean, the generic attack I just presented you is this, right? So the time complexity, it's 2 to the 65, because we twice have to enumerate 2 to the 64. And then data, we need this 2 to the 64 queries to the encryption oracle where we enumerate the tweak. And then, of course, we also have to store all the this T, right? So that's, I mean, it clearly breaks the 2 to the, or the 128-bit security, but it's not yet a practical attack, right? And then in the paper last year, we had this CCA, a boomerang attack, and this is still by far the fastest attack on half loop. But I mean, it's CCA, it requires physical access essentially. So you need encryption and decryption queries, and this somewhat translates to physical access to a radio. And what this tells you essentially is that if an attacker gets physical access, it's easy to recover the key without like any side channel attacks or whatnot, right? But okay, that's not so interesting maybe in practice, because maybe it's hard to get such a radio. More interesting is like the last attack, which, I mean, there are 2 rows in the table, right? That's because on the one hand, we have the theoretical side of the attack, and then we have the practical side of the attack, right? So we have this theoretical attack with time complexity 2 to the 56 and data complexity 2 to the 18. So that seems quite practical, but as it turns out, if you translate it to the practical setting, then the data complexity translates to that, like, an adversary has to eavesdrop for more than 500 years, and then, I mean, it's not practical anymore, right? So that's what we want to improve. We want to get this data complexity down to have a more practical attack. And if we want to get this down, let's start by getting the data complexity down in the theoretical setting. Okay, and that's the attack I mentioned at the beginning, right? Our new attack against half loop 24 with minimal data complexity. And actually for the new attack, let's first have a look at the old attack again. And there we use a related tweak in the key schedule, right? So we have the key schedule as before, and now we add this difference. So we have 2 encryptions, right, with related tweak, and that's the delta in the tweak. So the difference delta is in the 3rd byte, right? So 2 bytes no difference, 1 byte difference delta, and then no difference again. And then you can easily, because AES key schedule is linear except for this G function, but there's no difference here, so we can easily trace the delta through the key schedule, and that's all the wrong keys where we have a difference. And now let's plug it into like full half loop 24, right? So half loop 24 has 10 rounds, each round being key addition, SBox and linear layer, and of course a final key addition, and then that's all of half loop, right? So those are the red round keys are the round keys with a difference, and then actually the exact position of the difference I mark here. And now, I mean, it's rather obvious, right? If we have a delta here, let's maybe choose a plain text with a matching delta, because then we have a state difference 0, right? So the plain text difference and the tweak difference, so the thereby induced by the tweak difference, induced difference in the first round key cancel out, and then we have no state difference. Because there's no difference in the following round keys, we just skip the first rounds, right? So the first 6 rounds essentially don't matter, and we have a probability one related tweak differential, and we know that here before the addition of round key 6, we have a state difference of delta of 0. So let's remove all of this and only look at this. The idea of the old attack was that those 3 differences can cancel out essentially each other, and then we are left with a state difference 0 again. And actually this happens if and only if the ciphertext difference will be delta 0, 0, and that's something we can easily detect. But okay, we have to wait for it to happen. But if it happens, we can easily restore the keys here. But then because we have to wait, it increases the data complexity to this 2 to the 18, which we saw before, right? Right? But okay, so maybe for a moment, let's take a step back and like have a look. I mean, we know that here we have with probability 1, difference 0, and we have this round key. Okay, it doesn't matter really for the difference, right? If we can also have a look here, and then we know that we have difference delta 0, 0. And then there are only 4 round keys left, right? So that's only because each round key is 24 bits, that's only 96 bit of round key, right? And even more, if we like move round keys through the linear layer back, we see that this and this byte of round key also don't they don't matter for this difference, right? Or for this difference to be 0. So what this means is that there's a trivial attack with time complexity 2 to the 80 and data complexity 6, right? So I mean, it's a differential attack with probability 1. So like rule of thumb for data complexity of a differential attack is 1 over p, right? So that would be 1 in this case. But okay, of course, there's a small constant, and this is because 24-bit of plaintext and ciphertext together, I mean, even if you have 5 of them, that would in total be 120 bits, right? And that's not enough to uniquely identify 1 out of 2 to the 128 possible master keys, right? So we at least need 6, and actually the attack works with 6 pairs, with 6 plaintext cipher pairs, so 3 differential pairs. So the data complexity is optimal. And then this 2 to the 80, you could argue it's good enough, right? If your attacker is a state actor or something like this, 2 to the 80 is something that's probably possible, but also we can improve the attack. And the basic idea is that we can do a pre-computation and then have a lookup from this state difference here to the possible values of round key 8. And after this, we can also find this byte, and then we only have to brute force the remaining bits of the key. And that's then the improved attack. Okay, so let's have a look at all the attacks again. So those are just the attacks as before. And then those are the new attacks. So there are 2 flavors. So if we use 1 differential pair more, so 8 plaintext ciphertext pairs, we can reduce the time complexity by 2 to the 8. And then if we take this attack and translate it to the practical setting, we get only 2 hours instead of more than 500 years, right? And then time complexity 2 to 48. And now, instead of going into all the details of this attack, right? So how to build this table, and actually in the paper, we then like improve the attack, but not really improving it in the theoretical sense, but like for implementing it. So we split the large table into multiple small tables so that caching is more efficient and we can actually execute the attack a bit faster. And then we did, and then on our university server, it took like 12 days to run it. If you're interested in this, I again refer you to the paper, because now I want to explain how we do this step, right? How can we take this 8 plaintext ciphertext pairs and deduce that we need 2 hours of eavesdropping to run the attack. Okay, and for this, we have to look at the automatic link establishment protocol, so ALE. And I mean, of course, like if you remember before, we had this Casa funds, right, where they communicate with high frequency radio, and this on the picture, I mean, in the slides maybe looks easy, but in practice, of course, it's way more complicated, and that's why we have this automatic link establishment to automatically establish the link between 2 communicating parties. But actually, so in practice, we have a whole network, and all the people or all the units in the network share the same symmetric key. And I mean, for visualization, I use this Casa funds, the mascot of Casa. But remember that in practice, those are military units, right? So battleships, fighter jets, or infantry units. And then, of course, everyone in the network has a name. And usually, I mean, in crypto, if someone has a name, then we start with Alice, right? But here, actually, the name is important, and it will be a 3-letter name, or I mean, in the protocol, it's called call sign. So everyone in the network has a 3-letter call sign, and then, I mean, each character is 7 bits. So think of ASCII, but it's actually a reduced character set, right? We have uppercase letters, and then numbers, and then some special characters. Okay, so let's look at what happens if 2 parties, AAA and AAQ, want to communicate. So keep in mind, it's the handshake. So it's the very first message being sent. So Alice has a radio, sorry, not Alice, AAA has a radio and is pressing the button to communicate, and then the radio will send these messages. So in the messages, the plain text in the messages is 2 AAQ, and then again 2 AAQ, and then this AAA. So the meaning, I mean, it's quite obvious, right? It says that the messages are sent to AAQ, and then that the sender is AAA, right? Because remember, there's a network, so AAQ needs some way to see that the messages are meant for them, and then also needs to know who the sender is. And then each of these words, so each of these boxes is 24-bit, and that's where half-loop is then used to encrypt those messages. And then, of course, I mean, half-loop tweakable block cipher, right? So we have a tweak, and as I said before, we have the time, so the month, the day, the minutes, and the seconds. For some reason, no years, so after 1 year, we might get repeating tweaks, a word counter, and then the used frequency, like in the radio network, right? And we can assume that this frequency is fixed. So there might be a couple of possibilities, but not so many. Okay. And then, I mean, we have this word counter, right? So the first word is encrypted with the tweak word counter 1. Second, we have tweak 2. And third, we have not tweak word counter 3 for the third word, right? So this simply counts up, and this all is binary, and except for the frequency, which for convenience, I encoded in decimal. Okay, so now we're going to wait some time, right? And eventually someone else will send a message to AAA. And here, I mean, for the sake of the example, I have AAQ sending the message, but it could be anyone, right? So the important thing is that we have AAQ and AAA here. Because actually, the parts of the plaintext and the tweak that matter for our attack, right? Remember, we have this plaintext difference 0, 0, delta, and the tweak difference also 0, 0, delta, and then a bunch of zeros again. So it's in the third byte. And okay, I forgot to say this 2 and this are encoded in only 3 bits. And then we have 7 bits for each character, so that's 24-bit. So the last byte is this character, and then, okay, the least significant bit of the middle character. And then the tweakly relevant part is marked in red, so that's the third byte. And it's the least significant 4 bits of the minute and the 4 most significant bits of the seconds. So that's actually kind of perfect for our attack, right? Because our attack needs some arbitrary difference delta in the stuff that is marked red here. And so what does it mean? It means that the frequencies must be the same. So that's easy, right? I said that we can assume that the frequency is fixed for all of the network. The word counter must be the same. Well, that's also the case, right? So the first message, the first word here and here have the same word counter, and then For the second message, well, they also have the same word counter, right? It's just incremented by 1, and then also for the third one, so also easy. And then the messages must be sent in the same 16-minute bin, right? So the month and day, and then the uppermost bits of the minutes must be the same. So that means 16-minute must be the same, and that's kind of convenient for an attacker, right? Because you don't have to store your messages for ages. You just always look at 16-minute bin, and if you don't have a good pair in there, you can just throw it away. And then, okay, the seconds must be the same modulo 4, right? Because there is no difference allowed in the 2 least significant bits of the seconds. And I mean, okay, we have the assumption here that we just assume that the messages, so the last 2 bits of the second or the seconds in general will be like somewhat uniform, right? And then, okay, it will happen eventually, right? And then the only thing that really has to happen if this is fulfilled is that the difference we have here is matching the difference in the call signs, right? So here I have a 1-bit difference, which corresponds to 16, right, in decimal, and then it would match the difference of A and Q if you like encode A as 0 and Q as 16. Okay, and like again, let me point out, this is super convenient for the attacker. Of course, like whether this happens in the call signs, it depends on the specific network. And actually, like in a paper last year, we looked at some public high frequency radios, so where we could observe the call signs. And okay, it was not all the same, but sometimes there was a very high probability of this happen. Sometimes probability was not so high. So it will depend on the specific network. Yeah. Okay, so and then that's essentially the attack. And now, just very briefly, I want to show you the results that we have for half loop 48 and 96, so the larger versions. And there, I mean, again, we have this generic attack, which I already showed, right? It also works for half loop 48 and 96. And then we have, again, I mean, it clearly breaks the 2 to the 128 security, but I mean, it's not very practical, right? And then what we also do is we give this Demirciy Selçuk middle attack. And then with this, I mean, the time complexity is even worse, so it's not practical, but we can bring the data complexity down again, right? So, and this is maybe like, could be start of future work. And I mean, for half loop 96, it's only for reduced to 7 rounds, but I mean, it could be that one can start there and then improve the attacks there too. And yeah, then that's essentially it. Let me quickly recap the talk. So we looked at this half loop 24, right? A 24-bit trickle box cipher. And then we saw the differential attack with probability 1. So super efficient in terms of data, and then in time also quite efficient. And I mean, for your convenience, there are the complexities of the attack again. And then I just talked about this like translating the attack to the practical setting, and that, I mean, it's quite convenient for the attacker. Okay, so thank you.
Are there any questions? The guys with the mic.
Okay, yeah. Well, I guess the first lesson, I mean, so I don't know the designer of this, right? So if I remember correctly, it's someone from the HF community, and maybe let me first say, I mean, designing an insecure block cipher, if you're not really into symmetric crypto, right, or trickle block cipher, this will happen, right? So, I mean, I don't think that we can blame this guy for this, but then US military and NATO like standardizing it, that's something to blame, right? And then how to do it better? I mean, okay, so without like having any proof to that's how you should do it, I guess like the first approach would be to take a primitive you actually have, right? And then do a construction. So don't take AES and shrink it down, but take AES and do some generic like mode of operation or something, or trickle block cipher construction, right? And then you derive a secure block cipher. But then, I mean, for so small, block sizes, it's not trivial, right? So if you only have 24-bit block size, okay, no, maybe I just stick to this, but you only have 24-bit block size, like strange stuff happens, right? You might be able to just compute the DDT because, I mean, it's only 24-bit in size. And then if you like take random keys, it might be that you be able to see something. So, I mean, it's different application, but for randomizing caches, right? We have in like recently seen new designs like BIP and Scarf and stuff like this. So I would say for small block sizes, it's definitely like something that's not too clear, right? So there's room for improvement there.
Roberto?
So yes, so my comment was something related to my experience as a cryptographer in the industry. And I think in the military it's the same. A lot of people will tell you, oh, this design is nice, but why don't we use the AES box or the AES linear layer? Because it's standard. So just use any ASCON round and think, I mean, there is a reason the ciphers are done that way. It's not just because of the S box or the shape of the layer, but how. And I guess that's exactly the mistake they made. So inexperienced people, they just took something that is known, and then it must be secure. Otherwise, why would it be there? And that's a very common mistake I saw, well, not daily, but I would say half yearly done in the industry. The second thing, I would like to give an answer to our colleagues, how to design. In that case, I would use a Feistel with a function that expands a lot in order also to increase the number of S-boxes that are active and shrinks a lot before adding. I would do something totally insane like that. Maybe, just maybe, it could work.
Yes, I guess that's maybe nothing that should be answered just in like a comment, right? But maybe there are some papers to be written, yeah.
Let's thank the speaker once again. Our next talk, is propagation of subspaces in primitives with monomial S-boxes, application to rescue and variants of the AES. This is a talk by Aurélien Boeuf, Anne Canteaut, and Léo Perrin, and Aurélien is going to present.
So, yeah. What does this work? Oh, okay. Hello. The AES was designed to resist differential cryptanalysis, as I'm sure most of you know. In order to do that, its designers employed what they called the white wire strategy. By using components with low differential uniformity and highly diffusive linear layers, you can make your block cipher have the differential uniformity of a random permutation after just a couple of rounds. Now, this actually relies on a couple of generic assumptions, but I mean, you can see for yourself that in practice it works very well, right? Well, it doesn't work all of the time. This is the differential uniformity of an AES-like block cipher, and even after 80 plus rounds, it keeps bouncing. Before we get there, we have some work to do. First, I will give an overview of rescue and arithmetization-oriented primitives. Then I will talk about affine space chains, which is the main mathematical tool we use for our analysis. And lastly, I will present some designs that we made to exemplify our findings. So first off, what's an arithmetization-oriented symmetric primitive? It's a mouthful. Well, in the last few years, there's been huge developments in advanced protocols, such as zero-knowledge proofs, MPC, FHE. And all of these protocols aim to do very different things, but they all have one common similarity, is that they all rely in one way or another on the arithmetic description of the underlying functions. And if you use a symmetric primitive in one of these protocols, well, you can just plug in the AES or SHA-3 because these functions do not have a simple arithmetic description at all. So there's been a need for primitives that are designed with algebraically simple operations. So there's been a real change of like paradigm between the classic world where, all of the operations are just binary operations. You can make your functions be algebraically complex for cheap, for some definition of complexity. Most of the time it's defined over small fields like typically F2 to the 8, right, for bytes. And yeah, ADS, SHA-3. But now it's something totally different. All of the operations must be defined in an average with like multiplications, additions, arithmetic operations. So it has to be algebraically simple in order to be efficient with the overarching protocol. And also we have to work on sometimes we have to work on large fields. So for example, the prime field of an elliptic curve. Examples are MIMC and Rescue, but more and more are being developed. So Rescue in particular was designed with zero knowledge applications in mind. So we'll detail a little bit how this works. Zero knowledge relies on sets of constraints. So there's a bunch of different systems, R1CS, AIR, Blanc. Generally speaking, you want less constraints, but of course that could also mean less security. So generally speaking, say you have a mathematical function. First, you present it as an arithmetic circuit, and then from that circuit, you can define a set of constraints used by your protocol. Let's look at some components that are of interest. So the first one that was used in MIMC is X-cube. So it's perfect for these protocols because it's only 2 multiplications, essentially, very few constraints, but it has low degree. So you may become vulnerable to algebraic attacks if you use this. On the other hand, if you just plug in the AES box, well, it has high algebraic degree, no problem there. However, it has so much constraints, as I said before, that you can't really do anything with it. And the idea of the designers of Rescue was to use the function inverse of x cubed, so x to the 1 over 3. So this function has very few constraints because from the point of view of the set of constraints, y to the alpha equals x and x to the alpha equals y is equivalent. But at least in the direct sense, it has a very high degree. So that's the basis for designing Rescue. Rescue is like based on the AES, essentially. You have a nonlinear layer composed of S boxes that are monomials. So x to the alpha, where alpha is as low as you can get. Essentially, it's not always a permutation, but typically it's going to be 3, 5, 7. It's defined for any MDS matrix, any set of all constants, and any prime that is greater than 2 to the 64. And the idea of the designer's Rescue was to use every couple of rounds alternate between x to the alpha and x to the 1 over alpha. The argument being that by doing that, you do not have a function of low degree or of degree that increases slowly. And there are more justifications for these design choices. So the first one is, yes, you can have resistance against algebraic attacks by alternating these two S boxes. But also, you should keep in mind that x to the alpha can have very good cryptographic properties. Typically, for alpha equals 3, this is actually APN. So, I mean, this is really ideal. It has very low, it has low verification cost because if algebraic attacks have to rely on multivariate solving, and this isn't very efficient. And essentially, it's the right strategy that is being used. But we can ask ourselves the question, in this context, this is so different, are these security arguments, which are the classical security arguments, sufficient? First, I have to remind what differential uniformity is. The differential uniformity of a function is this. Most of you are familiar with this. So if you impose a difference on the input and a difference on the output, you can count the number of input outputs that verify those two differences. And if you take the max over all possible pairs of inputs and output of differences, then that's the differential uniformity. and it must be minimized as an argument against differential cryptanalysis. And prior to our work, there was some analysis of rescue. This is a graph, which is essentially it's a bunch of small instances of rescue that were generated, and the differential uniformity of the whole block cipher was measured. So for most of these curves, it behaves as you would expect. So it starts maybe a bit high, but then it very quickly reaches. So this is level 1. This is like the normalized differential uniformity. It should reach the one of our random permutation, ideally. But there is one curve that's a little weird. So it's like it goes down, then back up, then back down. So it would be one thing if it just didn't go down very slowly, but the fact that it goes down and goes back up, it almost seems like applying an additional round makes your function weaker, right? Something like that. So this is really weird, and we set out to understand this. And it's actually explained by what we call affine space chains of dimension 1. To see what I mean by that, let's write elements of this affine space, A plus the set generated by V, as all elements A plus X times V, where X is in FP. Then this is what's happening. So here, this is the whole possible space of my inputs in FP to the M. And there's one subset of inputs, which forms an affine space, which is mapped by one round non-linearly to another affine space, and then after another round non-linearly to a second affine space. But essentially, because there's the alpha and the 1 over alpha, they kind of cancel out, and so the function over 2 rounds is affine. So this doesn't happen all of the time, of course, but it can happen. So I'm going to explain why this gives so many solutions to differential uniformity, but essentially it boils down to the fact that the differential of an affine function is constant, right? So let's take an example of an input and fight space, AX. So f to the AX, I say this is 2 rounds, and it's an affine function. So when you do f of x plus difference minus f of x, the x is cancelled out, and you get a constant value. So the differential uniformity must be greater than or equal to p. And again, p is greater than 2 to the 64. So this is actually really big. But the high differential uniformities are one thing. We were more interested in the underlying affine space chains that were happening. In fact, this is a more general phenomenon that was happening under the hood. And actually, we're not going to talk about differential uniformities anymore until the end of the presentation. So this is what we mean by affine space chain. So I have an affine space A0 that is mapped by one round to an affine space A1, etc. to AN. When does this happen, right? So before I get into the details, let's take a look at an example to kind of show what's happening. I'm going to take the input affine space 00A plus the set generated by 1B0. So it's a little particular. You'll see why later. I can write all of its elements as X, V times X, and A, right? So first I apply the nonlinear layer, and this is the most important part. This is where everything works. So you can see that if I put everything to the alpha, I have X to the alpha, V to the alpha, X to the alpha, and A to the alpha. And I can factorize by X to the alpha to get this. And when X is in FP, this forms an affine space again. So the real issue is that the nonlinear layer maps some affine spaces to affine spaces. This is really what's bothersome. And it only relies on the fact that you have a full round of monomials. Just because everything's put to the alpha, you can like factorize X. That's why it's happening. Okay, so the whole set of affine spaces for which this works is what we call separable affine spaces. It's a special property where you say that an affine space is separable if it can be written as A plus the set generated by V, such that A and V have disjoint supports. So in other words, for every coordinate, either one is equal to 0 or the other. Let's take a look at some examples to see what I mean. If I take 1, 0 plus the generated by 0, 1, it's a separable affine space, right? Because these choices of A and V work. 1, 0, 0, 1, always one of them is equal to 0. 0, 1 plus 1, 1, 0 is not, but it's not sufficient to see that these joints these supports are not disjoint. In order to say that it's not separable, you have to look at all of the possible representants. And essentially, because the generating vector cannot have all of its coordinates, cannot have any of its coordinates at 0, you will need 0, 0 to be a possible constant part, which is not possible. So this space is not separable. And what about this one? Is it separable or not? Doesn't seem like it, but it is, because you can have another set of representants where the supports are disjoint. Okay. So now you can notice that the affine space I took to start with was in fact separable. After that, I apply the MDS matrix and I add the round constants. So at this point, it's not necessarily separable anymore, right? And yeah, this is the affine space we get at the end. So when is this separable, right? Because if it is separable, then the next round is going to be mapped to an affine space again. And we want to make this, to change this as long as possible, essentially. So you can voice this condition as, well, like this. And the choice of representants gives us an additional degree of freedom, which is represented by this factor lambda here. It's just saying that you can add any multiple of the generating vector to the constant part, and it would still be a valid constant part. So when does these two have disjoint supports? That is, in fact, our theorem. That the image of a separable affine space by one round of monomer SPN is an affine space, and the affine space we get is still separable if and only if there's these conditions, which we show as conditions on the round constants. So what we're saying essentially is that if you choose the round constants well, you can keep this chain going for as long as you want. In other words, there are weak constants. And we use this to come up with some weak and weird designs to exemplify what we say. And essentially, our point is that all of these designs all of these designs verify all of the usual classical security arguments. You know, the S boxes have low differential uniformity, the matrices are MDS, it's a white strategy, but there's this really weird thing happening because we're arithmetization oriented, right? We have come up with 3 kind of designs that we call, so stir is a weak instance of rescue. Snare is a tweakable cipher. So the point is that there is a secret weak tweak, so that if you choose the secret weak tweak, there is an affine space that goes through the whole cipher. It's based on the malicious framework. And lastly, we've come up with AES-like ciphers where, like we saw in the beginning, we can kind of manipulate the differential uniformity of the permutation and have it bounce up and down. So I don't have the time to talk about snare, but I will talk about the 2 others. So this is stir. It's actually rescue, right? Except the MDS matrix and round constants were chosen specifically so that there is an affine space chain over the whole permutation. So how does that impact security? Well, we chose the input and output affine space such that the last coordinate is always equal to 0. And this gives a bunch of solutions to the Kiko problem, constraint input, constraint output. Rescue is designed to be used in a sponge construction, which is why we argue that this breaks security. You can have collision with this and etc. So again, this relies on the fact that we chose specifically weak round constants. And that's it for stir. Now, before I move on to the last design, because we skipped snare, I have to kind of insist on the difference there is between an affine space chain and having an affine function. Essentially, in the beginning, we measured high differential uniformities because the function was affine, right? But you don't necessarily have that. You can have very well have, and in fact, this is what happens generally, an affine space chain without the function being affine for any number of rounds. But I mean, you can see this will be your typical affine space chain written as a kind of a polynomial function. And you see, if we have lambda equals 0 here, then as we saw in the beginning, the alpha and the 1 over alpha cancel out. And in fact, this will be our main condition for the function being affine. After 2 rounds, it's lambda equals 0 for this lambda. So we have a way of making the function affine. And this is what we call the AES-like cipher. Well, permutation just. So the S boxes are just the inverse. In this time we are over F2 to the N. And so we say it's AES-like because the S box of the ES is the inverse in F2 to the 8 followed by, well, actually, yeah, in the AES it's followed by an affine function on the bits, right? It was specifically so that it could not be represented by a simple operation in the large field. So we removed it to say, you know, this is closer to the arithmetization-oriented case. And the rest is, well, the linear layer is MDS. We had run constants. And the idea is the same thing as we've done before, choose the run constant so that there is an affine space over the whole permutation. But by having these special conditions, we can make it so that the function is affine every 2 or 3 rounds. So 3 rounds uses a special trick. We use an identity in F2 to the end with the inverse. But basically, by choosing the run constants well, we can have the differential uniformity spike in a way that we can kind of control after an arbitrary number of rounds. And so we chose to say that we can make Morse code with differential uniformity. So, okay, it's not really Morse code actually because there's no space character, but essentially, if you look at the bottom of the graph and you do the intersection with this horizontal line, then you can kind of read the dots and the dashes, and it spells out welcome to Leuven in Morse code over 94 rounds of this block cipher. So this is pretty funny, but we should also keep in mind that it is you know, highly irregular. That even though we have SPN S boxes, MDS matrices, the differential uniformity of the permutation is still bouncing up and down. So if anything, this shows that the usual security arguments we have for block ciphers are sometimes not enough. Which leads me to our conclusion. So as we saw, there are some weak round constants, but I have to say that you know, if you actually choose the round constant randomly, normally it is very unlikely that you will have an affine space chain that is longer than the minimal, actually. So essentially, the whole point that we're trying to make, so as I've said, and I will say it again, is that in this arithmetization-oriented context, the usual whiteware strategy is not really satisfactory enough. You know, we need additional arguments that can help us say that this kind of algebraic weird things do not happen. So what will be those arguments? I don't know yet, but we have to think about it as a community. And a little advertising this principle. So the principles behind these techniques, essentially, not just affine space chains, but in general, representing the first few rounds as low degree functions on specific inputs, can be applied to AOPs. So in fact, it's not necessarily, you can't necessarily have an infinitely expanding affine space chain in these over primitives, but you can use small chains to essentially improve algebraic attacks, right? By essentially, you skip rounds if you have affine space chains of the first couple of rounds. For more detail, see this paper on free lunch attacks, where we attack things like Arion and Griffin and break them. Thank you for listening.
We have some time for questions, if there are any questions. Roberta?
So thank you very much for your contribution, because it resonates a lot with me. So sometimes ideas come at the same time in a much more primitive way, but at this same conference. In our work on Karma V2, I was considering actually cosets, so basically affine subspaces, cosets of vector subspaces, and how they propagate. And I was observing that they almost never propagate of the same dimension after more than one round. So what could be the reason there is because our S box is not monomial. And the second question would be, is the fact that we generate our round constants programmatically with a linear feedback shift register something that might be fishy in your opinion?
So you're talking about Karma, right?
Karma, yes. I mean, we have also considering this, but the S box is not monomial. And we see that the dimension of any subspace always explodes. So spaces of dimension 1 are not mapped, except in very rare cases, to other cosets of dimension 1, and they always grow in dimension, almost always. And so is that because it's not monomial? Second, our round constants are generated, basically they are linear. So is that something that could be fishy?
Well, for the round constants, I think you will be very unlucky if the specific way you generate the round constants leads to invariant algebraic things. That would be very unlucky. Now, I mean, I don't know what boxes you're using. I mean, I guess there's a bunch of possible. It's not a monomial. I mean, for this kind of algebraic things, I think it's surprising to have invariant algebraic structures if your functions are not really algebraic. I mean, it's like if you take the ASS box, there's nothing like that because they introduced this affine function on the subfield, so they kind of break the. But I mean, I don't know why.
I mean, nowadays the constraints sort of force the polynomial construct S box to be nullified.
Okay, well.
For some reason, have a look at that. See that. So would it be a good criterion?
The criteria, well, I mean, I think you would have to look at specifically what spaces are mapped to the others and try to think of it like maybe as a polynomial system, something like that. I mean, that's how you would, I don't know.
It's very interesting. Thank you very much.
Are there other questions? I have a quick question. How do you convince me as a designer of a new cipher that you didn't install bad constants and your attack is not applicable?
Well, for example, I would try to generate my constants from a well-known kind of unswerving sources, like, I don't know, the decimals of pi or something like that. I mean, so you also, if you do something like generate round constants from a chain of characters that's like, I don't know, hello mom, something like that, that is maybe not the best kind of way of generating round constants, because you could say that you could have some degrees of freedom in how you make them. So in our case, we don't really, we make a point that we don't have too many constraints on our round constants. So sometimes I think you don't necessarily need to have lots of constraints to have your weakness. So how will you, I mean, I don't know, it's a good question.
Another question is how this translate into linear cryptanalysis. There's an ePrint report by Tomer Ashur and his students, Lukas, about doing something very similar in linear cryptanalysis. So can you translate this into linear cryptanalysis?
So I'm not sure how this translates to linear cryptanalysis, but at least for algebraic cryptanalysis, this directly improves like the modeling essentially. Linear cryptanalysis, yeah, I'm not sure how that would work. I mean, I haven't seen a lot of works on linear cryptanalysis on these arithmetization-oriented ciphers. Like just the fact that the fields are so huge, statistical cryptanalysis seems to just not work as well. Yeah.
Are there any questions? If not, that's the thank the speaker and the previous speaker again.